Hello everyone. Hey guys, today in this session I am going to discuss with you electronegativity and all about its applications. So yeah, this is very important to know what are its applications. So guys, before this session starts and I talk about all the things all together, let us play a game. Yeah, why? Okay, absolutely. So I want to play with your tug of war. Okay, so let's say this is my rope, and here this is my left hand, this is my right hand, and I want to pull this rope. Now I want to see, because I don't have a team of like 4 or 5, I'm just a single person here. So I will be playing this game with me only. So if this is a rope and I want to pull this particular rope, and this is my left hand and this is the right hand, so I want to see who is more powerful, who is being able to pull this rope towards itself. So yeah, I'm a right-handed person, so my right hand is more powerful, and so yeah, this wins, right? So what is this? Guys, this is simply electronegativity. Yeah, actually. So here, whenever there will be a bond formation, there is a pair of electron. So whosoever, let's say this is a element A, this is a element B. So whosoever will pull the shared pair of electron towards itself. So if this was A and this was B, who is more electronegative? So anybody, any of the species that will be more electronegative will pull the shared pair of electron towards itself and hence become more electronegative in nature. Yes guys, so this B is more electronegative. So as in my case, my hand is more electronegative, my right hand. Okay, so electronegativity is simply a pulling of shared pair of electron. Okay, so guys, it's a relative property. So I can say that as compared to my right hand or left hand, my right hand is more powerful. So it's a relative property. For the electronegativity, there is a compulsion that there must be a bond formation. Okay, so this is a property which could only be applied to a molecule. Okay, so whenever there will be a bond, there could be an electronegativity principle that lies. This is the only property, which is not atomic but molecular in nature. So let's move ahead and let's know that what we are all going to learn about in this whole session. We will be focusing over that what is electronegativity, which I already told you, the scales of electronegativity, how we can measure the scales. There could be the Mulligan scale, Alfred-Roscher scale, and the Pauling scale. Okay, what are the factors that affect the electronegativity, whether the electronegativity increases or decreases? Who plays an important role in determining it? Electronegativity values, you might know the fluorine is highly electronegative. How we do say the fluorine is highly electronegative? Fluorine is highly electronegative as related to the oxygen. Okay, so whenever there will be a bond formation, we can say that this is more electronegative. So the electronegativity values are given by Pauling. So we will be having a focus on that. Most importantly, this is okay, all this you need to know, but the most important that you need to know is about its applications, because if you know, then you will be able to do the questions related to the nomenclature. Okay, why we always say sodium chloride, why we don't say sodium chlorine or chlorosodium, right? So there must be a reason, no, why the nomenclature is something like sodium chloride is only there, hydrogen chloride, why we are putting chloride, why the chlorine is later on, and the why we are writing H in at first and the chlorine at last in the case of HCl. So what's the reason behind it? What is the type of a bond, whether a bond is ionic or covalent, how we can determine the nature of bond, how we can determine the acidic strength depending upon the electronegativity values, basic strength. Many of the students are always confused what is this acid base behavior, because they are not able to understand, because they don't know the electronegativity principle. Okay, so here we are going to have a focus on all such things, and the last is the bond length. Okay, so guys, yeah, this is a periodic table and we need to learn the periodic trend of electronegativity in the whole table, whether what happens from left to right or what happens from top to bottom. So let's move ahead so that we will be able to focus on each and every point. First of all, what I told you, it's a relative property, okay, in relation to this and this. It's a molecular property. There must be a bond formation, while the ionization energy, the electron affinity, they all are atomic property. They are the properties of a single atom. Okay, so As I already told you, what is the general definition? The tendency or the power of an atom to pull the shared electron pair towards itself in a single bonded molecule. Okay, so there must be a single bond. So if any of the species is more powerful to pull the shared pair of electron, is said to be more electronegative. Okay, so guys, electronegativity is a relative property. It has no unit, and there is no direct method by which you will be able to evaluate what is electronegativity. Okay, so there is no such direct method by which you will be able to evaluate the electronegativity values. Okay, but here we do have some scales, and what you need to know about them is, let's go there. So the first is the Pauling scale. Pauling said that the difference in electronegativity values we can determine by the bond energies, Let's say here I am having any molecule like H2, okay, and here in the case of H2, this could be as H positive, H negative, or this could be as H negative to H positive. Okay, so we need to know that what is the bond energy. So this is a simple molecule H2, there is no heteroatom, they are the same atoms. But if we do have HCl, if we do have H2, if we do have Cl2, then what can happen? There must be the bond energies of every bond. Okay, that is the energy required to form any bond. Okay, that is known as the bond energy. So the bond energy of AB bond, bond energy of AA bond, like atoms, like atoms. Okay, so these are the bond energies. So depending upon the bond energies, we can determine the electronegativity values. Okay, we can determine the difference in electronegativity of A and B. Okay, so if I am having any kind of molecule like HCl, so what I can do is I can do a simple calculation, that is the delta for this electronegativity of hydrogen and the electronegativity of chlorine. The difference in electronegativity of hydrogen and chlorine is equals to 0.208 under root the bond energy which is being required for the HCl minus under root the bond energy which is required for the H2 molecule multiplied by the bond energy which is being required by the Cl bond. Okay, so these are the bond energies required by these bonds. If we do all the calculation, then we will be able to find out the difference in electronegativity values. Okay, so this is being said by Pauling. Okay, so here usually whenever we find out the energies in physics we use electron volt per atom, but here in chemistry, rather than calculating in the terms of electron volt, we will be calculating in the terms of kilojoule per mole. Okay, so if you use kilojoule per mole, so 1 electron volt is equals to 96.5, or this is this. So this is simply a calculation, okay, but we need not to go into any such calculation. So it is a simple scale which define the electronegativity on the basis of bond energies. Okay, on the basis of bond energies, the bond energies between the difference between the bond energies of HCl we can determine by this way. Okay, so here we can say that the electronegativity values could be determined in the terms of kilojoule per mole. Okay, so if you will multiply this 0.208 by this 96.5, you will be getting this 0.1017, and so therefore this value will be converted into the kilojoule per mole. Got it? So now we do have the another scale as well, which is known as the Mulligan scale. So how Mulligan explained this electronegativity principle? Mulligan said that this is an average of ionization energy and electron affinity. Okay, you know what is ionization energy? This is ionization energy. So ionization energy, you might have gone through my previous lectures, means if any of the species has a tendency to lose electron, okay, so the energy required to remove electron from an isolated gaseous atom is ionization energy. So this species is tend to give the electron, and electron affinity when any of the species is tend to gain the electron. So if this electron can be gained by any of the species, then this can become M negative. Okay, that is whatever the change in internal energy when there will be a gain of an electron in an isolated gaseous atom is the electron affinity. So here what is happening when we are talking about the electronegativity? One is pulling the electron. So if one is pulling the electron, the other is giving the electron, no? Okay, if one is taking the electron pair, then the other is giving the electron pair. So we are saying that if this metal or this species is giving the electron pair, so this is, let's say this is A, and the one who is pulling the electron pair, let's say this is this, okay, who is pulling the electron pair. So we said that okay, the electronegativity can be determined by the ionization energy, the one who is giving the electron pair, and by the electron affinity, who is pulling the electron pair, and so therefore we just do the average of it and we will be able to find out the electronegativity value. So this is as per the Mulligan scale. Okay, so if we do all such calculation in the terms of electron volt per atom, but you will convert into kilojoule, this will become multiplied by 96.5. If you want to convert it into kilocalorie, then you have to multiply it by 23.06. So it's just a conversion. Here I have given you what this 1 electron volt is all about. Okay, so this way we can do the conversion. Okay. So this is as simple as that. So when we have found the relationship between the Pauling scale and the Mulligan scale, we found that the Mulligan scale is greater. The values given by Mulligan scale were 2.8 times greater than that of the Pauling. You just do the cross multiplication, you will be able to get it. So the electronegativity values that we got from the Mulligan scale were 2.8 times greater than that of the Pauling. So Pauling's value are smaller and the Mulligan's value are larger. But guys, let me tell you, out of all those scales, the scale which is being more in use is the Pauling scale, means the scale that we have first taken, which is based on the bond energies. Now here we have the third scale, which is the Allred-Rochow scale. So what does he says? He says that, this scientist says that by determining the Z effective and the radii of an atom, we can determine the electronegativity values. So what does this mean? Simply, so here I am saying that A and B is more powerful to pull the shared pair of electron. Why B is more powerful to pull the shared pair of electron? Then the Allred-Rochow says that your B is having more Z effective, your B is having more attraction for the last shell electron. So if the Z effective increases, the size of the atom decreases. So what I am saying that if the Z effective increases, the radii of an atom decreases, and if the radius of the atom decreases, the size shrinks. So when the radius of the atom decreases, it becomes more powerful, है ना? So it will become more powerful and will pull the shared pair of electron towards itself. So that's how we said that okay, if you are talking about the electronegativity increases the Z effective. As the Z effective increases, as the effective nuclear charge increases, the electronegativity increases. Okay, and as the radius of the atom decreases, as the size becomes smaller, it will be able to attract the electron pair more strongly. Okay, because the distance between the nucleus and the shared pair of electron, है ना? So they will become more approachable, and so therefore it will pull the shared pair of electron very easily. So as the radii decreases, the electronegativity increases. So here we found that there is an inverse relationship and there is a direct relationship. So Allred-Rochow has given us a relationship that says that electronegativity can be is equals to 0.359. Yeah, somehow they experimented and then they derived this expression which says that 0.359 Z effective divided by R square plus 0.744. Okay, so this is the expression. You just need to learn the expression. No need to go through that how it is being derived or something. It is just that for you. Okay, so by determining the Z effective, that is by the Slater's rule, okay, we need to find out all the electrons which needs to be included, because it is a matter of bonding. Okay, so we can't leave the last electron while determining the Z effective from the Slater's rule. Okay, so we have to basically include all the electrons because we are talking about the bonded pair of electron. Okay, so this is it. So ultimately, what we conclude? We conclude that electronegativity is basically tug of war. In my terms, electronegativity is tug of war. So here any of the species A or B, whosoever will pull the shared pair of electron is said to be more electronegative. Okay, and the one who is not able to pull will be more electropositive. Okay, so this is it. This becomes positive, this becomes negative. And so therefore there were three scales as per the Pauling scale. So what is my take from the Pauling scale? Okay, Pauling has talked about the electronegativity values on the basis of bond energies. on the basis of bond energies. He just said that if I take my take from Mulligan expressed the electronegativity values on the basis of ionization energy and electron affinity. He just said okay, they are the average of ionization and electron affinity, one is giving, one is taking, kind of thing is happening. And the Alder-Rashaw said that okay, this would be directly proportional to Z effective as the Z effective increases and the radii, and inversely proportional to the radius. Okay, that is R square. Okay, so yeah, you can go through with the expression. So ultimately on such particular points they have given their definitions. Okay, they have given their scales, and from all such scales we have to go, the most used scale is basically the Pauling scale, and I told you Pauling's values are smaller as compared to that of the Mulligan's value. Okay, so overall we can say that what would be the factors that affects the electronegativity? We can say that Z effective, of course. Alder-Rashaw has also talked about the Z effective. So as the Z effective increases, the pulling tendency for the shared pair of electron increases. Okay, so the electronegativity increases, directly proportional. Principal quantum number, we know that as the value of, this is my nucleus, these are the number of shells. So as the n value increases, n is equals to 1, 2, 3, 4. So n is equals to 4, the size increases, n increases means size increases. If the size increases, if let's say this is the shared pair of electron, so if the size increases, will it be able to pull the shared pair of electron towards itself? No, because the nuclear attraction decreases, there is an increase in distance. So this distance increases, so this will not be able to pull the shared pair of electron very easily. So ultimately we can say that the electronegativity decreases. So n and electronegativity are inversely proportional to each other. I'm sorry for that. So we can say that if n increases, the electronegativity decreases. Chalo. So here we move on with the another factor, that is atomic size. It's very obvious, just now I discussed with you. Size increase, electronegativity decrease, means inversely proportional. Okay. Now what is the percentage of S character? This is the most amazing thing. Okay. Guys, whenever we talk about electronegativity, you remember this point, you remember this point, you remember this point, but mostly my students, my dear students, forget about these 2 points. Okay, please guys, try to understand. As the percentage of S character increases, you know the hybridization, sp3, sp2 or sp hybridization, here you have the 25% of S character, only 1/4 S is there. Here we have 1/3, means 33.33% of S character. Here we have 50% of S character. So as the S character increases, this becomes more electronegative. So if I am having a carbon which is sp3 hybridized, if I am having a carbon which is sp2 hybridized, if I am having a carbon which is sp hybridized, so this carbon which is sp hybridized, okay, is having 50% of S character, and hence this becomes highly electronegative. So as the percentage of S character increases, the electronegativity increases. Please do understand this point. Okay, why is it so? Guys, you know S orbital is very spherical in shape, and the p orbital is dumbbell shape, it is lengthier. Okay, it is more directional. So S orbital has more penetration effect. So when you will be having more percentage of S character, means you have more penetration power. More penetration power means the electron density is more close to the nucleus. Okay, and this will be having more effective nuclear charge. Okay, so because the orbital tends to get relativistic contraction would be there. Okay, so here whenever the S character increases, the electronegativity increases, but the p orbital goes away from the nucleus, d goes more away from the nucleus, f is much diffused. Okay, so this is the point. Oxidation state, so please mark them as a star and always remember the points. Oxidation state, as and when the positive oxidation state increases, let's say Here I am having A positive, I am having A plus 2, I am having A plus 3, I am having A plus 4, I am having A plus 5. As the positive oxidation state increases, you know, the size of the atom decreases. I already talked about the ionic sizes, right? The size decreases. So if the size decreases, if the positive oxidation state increases, if the oxidation state increases, the size decreases. The size decreases means the effective nuclear charge increases. The effective nuclear charge increases, the Z effective increases, and if the Z effective increases, the electronegativity increases. Okay, so anything which is getting smaller in size because of the higher oxidation state will be able to pull the shared pair of electron more strongly. So ultimately we can say that oxidation state and electronegativity are directly proportional to each other. Okay, so oxidation state increases, the electronegativity increases. So I hope you understood all these 5 points very well. Okay, so because when we are able to understand this, then only we will be able to do many of the questions from the inorganic and organic section. Okay, chaliye. So let's move ahead with the electronegativity values which are given by the Pauling scale. If you would see here, okay, let me discuss with you. You all know that we do have in the period number 2, we do have lithium, beryllium, boron, carbon, nitrogen, oxygen and fluorine. So have a look over them. So what you will see, if you will see all these elements, you will find that here the electronegativity values are increasing in the period number 2, right? Lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine. So the value for the fluorine is 4.0, 4.0, this is 3.5, this is 3, this is 2.5, this is 2.0, this is 1.5 and 1.0. So there is just a difference of 0.5, 0.5, 0.5 difference, 0.5 difference, 0.5, 0.5, 0.5. Just from a difference of 0.5, we can easily write these values. I would recommend you guys to learn all these values. Okay, it's very simple. 4, 3.53, 2.52, 1.51. Okay, very simple. So we can see that in the period number 2 elements, as we are going from left to right, as we already know that the Z effective increases, and as the Z effective increases, the size decreases and the electronegativity increases. Okay, simple. So yeah, we can say that the electronegativity values are increasing. Now, what about the other elements? Now here I will be telling you about, let me erase all the links from the slide. Now let me focus over few other elements. I will be telling you in an easier way. So these are my period number 2 elements. Now after nitrogen there comes phosphorus, oxygen there comes sulfur, after fluorine there comes chlorine, and after chlorine there comes bromine. Okay, only these elements we have to learn. Okay, that is phosphorus, chlorine, sulfur and chlorine and bromine. Okay, other than that, Pauling has not given electronegativity value for any other element. If you talk about, ma'am, what happened for the arsenic, what happened for the selenium, no. The Pauling has not given any values to such elements. Okay, so here what we notice is that for the after fluorine, when we go from top to bottom, now you see here you said the size is decreasing. The size is decreasing, the electronegativity is increasing, right? Because the Z effective is increasing. But from the fluorine to chlorine, the size increase, and chlorine to bromine, the size increases more. So the electronegativity will decrease because N value increases, so electronegativity decreases. So fluorine, if the fluorine is 4.0, then the chlorine will become 3.0. Okay, the bromine will become 2.8. So there is a difference of 1, complete 1. So 4 to 3, 3 to 2.8. Okay, then the difference is becoming negligible. Okay, so this is it. Now you please compare with the sulfur. So if it was 3.0, then what it would be? Of course, now here from the oxygen to sulfur, the N value is increasing. So if it has to be less than 3.5. So what it would be? Guys, sulfur is going to be 2.5. So if this is 3, this is 2.5. Again a difference of 0.5, and the phosphorus becomes 2.1. 2.1. So these are the values you please learn. Okay, chlorine is 3, sulfur is 2.5, difference of 0.5, then the phosphorus is 2.1. Okay, and if you would see bromine, this becomes 2.8. Okay, now there is one more element that we need to learn is hydrogen. Hydrogen value is also 2.1. So you can see that hydrogen and phosphorus, they have a same electronegativity values. Okay, they have a same electronegativity values. So if I ask you, if I draw the structure of a methane, that is CH, 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 then who will pull the shared pair of electron? Then the carbon electronegativity values is 2.5 and here the hydrogen value is 2.1. So who will pull the shared pair of electron? Basically carbon will pull the shared pair of electron. Okay, because of more electronegativity value. But ultimately the difference is very less. So we cannot say that this bond is going to be broken. Okay, so whenever there will be a difference in electronegativity, whenever there will be a difference in the power of the atom A and atom B, then only there would be a breaking of bond, then only there will be a pulling of shared pair of electron if one is more powerful than the other. Okay, so there must be a good fight, है ना? If there is a fight, then it has to be a good fight. Okay, chalo. So now guys, what would be the variation that we have focused? We could say that when you are moving from left to right, the electronegativity is increasing. Electronegativity is increasing because the size is decreasing, or you can say the Z effective increases, the radius decreases, the electronegativity increases. Again, it's a repeat. What happened when we move from top to bottom? When we are moving from top to bottom, guys, n value increases, increases, then size increases a lot, the electronegativity decreases. Okay, but here the Z remains constant, only n increases. Only n means the principal quantum number, the atomic number increase, the principal quantum number increase. Okay, Z effective remains constant. This is a point which has been taken from our previous sessions. Okay, chalo. So here we move on. So we all understood that what happens in the electronegativity values. So guys, my take from all this is, okay, there were 3 scales, but out of all these scales are to help us to determine the electronegativity values, but from all the scale, I just have to go with the Pauling scale. Okay, so with the Pauling scale is all good, we know the electronegativity values. Okay, and so is this electronegativity principle can be applied to period number 3, 4, 5 or 6 elements? No, not at all, because as the size of the atom increases, there is no enjoyment in playing tug of war. Okay, so a tug of war, a pushing or pulling of electron can better happen in the atoms which are smaller in sizes. Okay, so basically in the elements of period number 2 or period number 3, that's it. Okay, and then later on electronegativity values are not going to be no point of considering the electronegativity values. Okay, now I will be talking about the applications of electronegativity. Guys, as I told you at the beginning of the session, we have 5 things to learn. Nomenclature, how we can write down the nomenclature. The other would be the ionic or covalent bond. The third would be the acidic character, basic character, and the bond length. So let's begin with the nomenclature first. Nomenclature. Why, you might be amazed to know why the element is OF2, why I cannot write F2O. But what's the reason that I'm writing OF2 and I'm writing Cl2O? Why I cannot write OCl2 the same way? Why these two cannot be written in the same way, in the same format? Why? Because there is a certain pattern which is known as nomenclature. The nomenclature says that whenever you have to write the name of any compound, please write the positive part first and then the negative part. Means the positive species, the electropositive species will come first, then the electronegative species. So if I am talking about the OF2 molecule, in the case of O and F2 molecule, oxygen is 3.5 and fluorine is 4.0. So who is more electronegative? Fluorine. So fluorine will go right hand side and the oxygen which is less electronegative will come here. So what is the formula? OF2. So yeah, this will become OF2. Okay, so that's how we can only write it as OF2, we cannot write it as F2O. That will go wrong. Okay, so more electronegative atom is written with suffix, and whenever we have to write the name, then the element which is more electronegative will be written with a name either. So we will be writing it as fluorider, fluorider. Okay, and here we have an oxygen which is a less electronegative element, so this will be written as it is. So if it is oxygen, it will written as oxygen, oxygen fluoride. Okay, if you want to know, ma'am, why the formula is OF2, why the formula is not OF, guys, oxygen valency is 2 and the fluorine valency is 1. So if you will do the cross valency, this comes out to be OF2. Okay, so let me take another example. That is the example of Cl2O. If you are talking about that you have to form any of the compound of chlorine and oxygen, then Cl and O. So Cl, the electronegativity value is 3.5, and if you would see chlorine, this is 3.0. You remember, fluorine was 4, chlorine was 3, right? So who is more electronegative? Oxygen. So the species which is more negative will be on right hand side, and the species which is less electronegative will be on on left hand side. Okay, so the formula will become ClO. The valency of chlorine is a, now I can talk about the valency. The valency of chlorine is 1, the valency of oxygen is 2. So when you do the cross multiplication, this comes out to be Cl2O. Okay, so this is the way. Okay, this is a less electronegative and this is more electronegative. So now how to name it? So whenever you have an electronegative species, you have to put "-ider". So I will be writing this as oxider, oxider, and the chlorine will remain chlorine. So this chlorine will remain chlorine. So this is how many chlorine? 2 chlorine. So we can say that dichlorine oxide. Okay, so this is the way how we can write down the nomenclature. Okay, so I hope you all understood. Okay, so anything which is more positive will be on left and the electronegative will be on right. So this is the way that electronegativity principle teaches us. Now what about the nature of bond? Guys, simple funda. As per Pauling said that whenever the difference, whenever you are talking about the delta, the difference in the electronegativity values, if this comes out to be greater than 1.7, means A and B, there is a much difference between A and B. A is very small, B is very larger, and A is very electronegative, and the difference is greater than 1.7. Then A will pull the shared pair of electron and this will be broken. And if this will be broken, means this is ionic. Okay, so this is ionic. So if B is more powerful, then this will become negative and this will become positive. So the bond will be broken completely. Means I can say that in the A and B, the bond will be broken completely, and so therefore we can say that the bond is ionic. Okay, if the difference is less than 1.7, then if the difference between A and B is less than 1.7, so they will not be able to break the bond. This pen will remain there. This will not be able to be broken. Then what will happen? Then what can happen? If this is not going to be broken, this will be just be shifted. So this means that the electronegativity, because of the less difference in electronegativity, the electrons will simply be shifted. So I can say that this is negative and partially positive. I cannot break the bond. Okay, so it is just remain a covalent bond, but the electron density will get shifted from A to B, means the electron will be towards more B. This is it. Okay, but the bond remains covalent. Okay, but if the electronegativity value difference is 1.7, then we can say that it is 50% ionic or 50% covalent. So as per the Pauling, we got the value 1.7, but guys, there came an exception, or you can say an abnormality. So what was it? Let's have a look. If I am talking about HF, fluorine is 4.0, hydrogen is 2.1. So there is a difference of 1.9, 1.9. So if the difference is 1.9, means greater than 1.7, then it has to be ionic. Then HF has to be ionic. But we found that HF is covalent. Oh, so for the 1.9 value it has to be ionic, but it is covalent. HF hydrogen fluoride is covalent, so Pauling method failed. So whatever is being given by Pauling has been failed. So we can't go with the Pauling's value. Then after, we have the another scientist who is Henney-Smith method. Henney-Smith has given us a value which is 2.1. So Henney-Smith says that if your difference is greater than 2.1, then only a molecule is said to be ionic. Okay, if there is a difference of 2.1. Let me say that if I take Li and Cl, LiCl, you know the chlorine is 3.0, okay, and the lithium is 1.0. So there is a difference of 2.0. So 2.0 is less than 2.1. So this is covalent. So this is more covalent. So lithium chloride is more covalent. Okay, but if you will be talking about LiF, here the lithium is 1.0 and the fluorine is 4.0. The difference is of 3.0. So LiF is more, the lithium fluoride is more ionic. Why ionic? Because the difference is 3.0, which is greater than 2.1. So whenever the difference comes out to be greater than 2.1, the molecule is said to be ionic. It's very obvious if they have so much of electronegativity difference. Lithium is very poorly electronegative and fluorine is highly electronegative. So then the fluorine, because of its relative power, relative strength, the fluorine will pull the shared pair of electron towards itself, and this will become Li positive and this will become F negative. Okay, so this is being said by Henney-Smith. So he has given the value 2.1, 2.1, 2.1. If the difference is less than 2.1, it will remain covalent. So first of all, let me tell you one of the factor. None of the bond is purely ionic or purely covalent. None of the bond, okay. It's not about that NaCl is strongly ionic or like completely 100% ionic or HCl is 100% covalent. No guys, no bond is purely ionic, purely covalent. It is just that uh, who is in majority, right? Who is dominating? Okay, so there could be a more ionic character, there could be a more covalent character. If there is a presence of more ionic character, a compound is said to be ionic in nature. If there is a more percentage of covalent character, a molecule is said to be covalent in nature. Okay, so it's just that what is greater? Okay, and in pure form they cannot be ionic or covalent. So we have learned about the two things. For the first is nomenclature and the second is about their ionic or covalent character. Now here comes the acidic strength. So this is an amazing topic. So guys, I will be talking about the acidic strength for the hydracids. Okay, hydracids, what are hydracids? Any of the species when form a bond with the hydrogen, whether it is NH3, it is PH3, NPASH3, or you can say that we have nitrogen here, let's say we have H2O, we have HF, okay, so all these are species. So any of the element that forms a bond with the hydrogen is known as the hydracids. So we know one of the definition of acids, that the acids are proton donors. Acids are proton donors. So any of the species that will give its proton very easily is going to be most acidic. Okay. So to give proton, a bond has to be broken, right? A bond has to be broken. Now you see, you have hydrogen which is 2.1, fluorine which is 4.0. The difference is of 1.9. Okay, difference is of 1.9. Is this ionic? No. Here the bond is not going to be broken completely, and the HF is not going to give its hydrogen easily. Now what about H2O? In the case of H2O, if you would see H and O, oxygen is 3.5, hydrogen is 2.1. So the difference is of I can say 0.9, I can say 3.5, no, 1.4 something, right? The difference is of 1.4. Okay. Now here the nitrogen and hydrogen, if you would see the difference, hydrogen is 2.1 and the nitrogen is 3.0. So the difference is of 0.9. Okay. So which has a more tendency to give the H positive? None of them is ionic, all are covalent because the difference is less than 2.1. If the difference is less than 2.1, of course they all are covalent. They all are covalent hydroacids. But my point is, who has more tendency to give proton, which bond can be broken very easily. So guys, here we found that the difference is higher, 1.9, 1.4 and 0.9. So 1.9 is a much electronegativity difference. So if I ask any of the species who can give the proton easily, yes, HF can give the proton easily. So we can see that as the electronegativity increases with respect to the hydrogen, as the electronegativity of the element increases, the tendency to give the proton increases. Okay, so we can say that as the electronegativity increases, the tendency to give proton increases. The tendency or the behavior to give the H positive increases, and so therefore we can say that the acidic strength increases. So ultimately we got a relationship: as the electronegativity increases, the acidic strength increases. Okay, so this is what we can apply. Now if you ask me what happened when we go from top to bottom, okay, so when we go from top to bottom, guys, from top to bottom we cannot apply the concept of electronegativity, because when we go from top to bottom the n value increases a lot, and so therefore the size increases much. Okay, so when we are going from top to bottom, the n value predominates. So if n is increasing a lot, then absolutely our size is increasing. Okay, so if you would see in the case of the nitrogen, phosphorus, arsenic, antimony and bismuth, then what you will be finding is that the size of the bismuth is so large, and this hydrogen is very small, so they will be having a very poor overlap. Okay, the orbital overlap will be very poor, right? The distance between the nucleus of bismuth and hydrogen will be very large, so this bond becomes weak, because of course the Pauling has also given the electronegativity values on the basis of bond energy. So here the bond becomes very weak, and as the bond becomes weak, the bond will be broken very easily and can give you the H positive easily. Okay, so if you would see the comparison in the case of NH, PH, then ASH, SBH and BIH. So if you will see the bond length is increasing. So guys, as the length of the thread increases, the length increases, it becomes easy to break that bond. And if I'm talking about a very small bond, is it easy to break it? No. But if the bond becomes larger in length, it becomes easy to break it. Okay, so here this bond is going to be broken very easily, and so therefore this will give you the H positive relatively easily, and this will be more acidic. So the electronegativity factor can be applied across the period. Across the period you can apply the concept of electronegativity, because Pauling has also given us the electronegativity values across the period. Pauling has not talked a lot about the along a group. Okay, so across the group, along a group, the size factor dominates. So if the size increases, the bond strength decreases, the acidic strength increases. Is it clear? Okay, so we can conclude that if you are talking along a period, there will be polarity. Polarity means electronegativity difference. Okay, but along a group, the size factor or the bond strength. So these are the things that we have to focus. Okay, so ultimately we can conclude that when you are moving from carbon, nitrogen, oxygen, fluorine, the electronegativity increases, the acidic strength increases. But as you are moving from carbon to silica, germanium and SN, the size increases, the bond strength decreases, hence the acidic character increases. This is it. So got it? Electronegativity is directly proportional to acidic character. So this is the conclusion that we have drawn. Now, what about the basic strength? Guys, we found that just opposite. It's very obvious. Acids and bases are just opposite of each other. If the acidic character increase, of course the basic character decrease. Here we found that the electronegativity is directly proportional to acidic character. Then obviously electronegativity is inversely proportional to basic character. Okay, so if acidic character increases, the basic character decreases. Okay, so yes, absolutely. Okay, so chalo, let's have a look over that what happened and why the basic character is decreasing as the electronegativity is increasing. What has happened? Shit. Just a minute. Okay, so what about all this? Let's have a look. Electronegativity increases. Electronegativity increases means the tendency to pull the shared pair of electron increases. So here the electron gets very tightly bounded. Okay, so if I am talking about the nitrogen, I am talking about the oxygen, I am talking about the fluorine. So fluorine has a tendency to keep its electron more tightly held by the nucleus. Okay, so as the electronegativity, because its electronegativity value is 4.0, so as the electronegativity increases, electron gets tightly bounded by the nucleus. The nucleus will hold the electron more tightly. Okay, and if the electrons are more tightly held, they will be less available for donation. They will be less available for donation, and so therefore basic strength decreases. So actually you need to know what is base. A base is the one, base is a electron donor. A base is the one who is an electron donor, or you can say that this is a proton acceptor. Any of the species that can give its electron easily, है ना, to whom? To H positive. If any of the species, let's say this is B negative, if this can accept the proton very easily, when this can accept the proton very easily, when it has a tendency to give the electron pair to the vacant orbital of the H positive. Okay, so if the electrons are easily be able to donate, then the basic strength increases, and if they are less available for donation, the basic strength decreases. Simple that. So here we have taken a question. This is a nitrogen who wants to give its electron pair, nitrogen who wants to give its electron pair, and the nitrogen. The difference is this nitrogen is sp3 hybridized. If you would see, this nitrogen is sp3 hybridized. I must write this arrow there. Okay, the hybridization of nitrogen. This nitrogen is sp2 hybridized and this nitrogen is sp hybridized. So we want to see the nature of this nitrogen, whether this will be able to give the electron or not. So now guys, here the S character increases. As I told you, percentage of S character increases, which is 50% here. So S character increases, electronegativity increases. Electronegativity increases means the tendency to keep the electron pair more tightly increases. So if this nitrogen will keep the electron more tightly, then this will not be able to donate. So if this will not be able to donate, then we can say that the basic strength decreases. Okay. So as the electronegativity increases, the basic strength decreases. I hope you got the point. Okay, so here the percentage of S character was 25%, this was 33.33%, and this was 50%. So as the percentage of S character increasing, the electrons are more tightly held, they are less available for donation, and hence the basic strength decreases. So this is the fourth point, fourth application, and the last application is the bond length. What happens in the case of a bond length? So if you go through with all those lectures, I have just uploaded the 5 lectures on periodicity. Okay, so first lecture tells you about the basic concepts like shielding, penetration, what is their effective. The another tells you about the atomic size. The third lecture tells you about the ionization energy. The fourth lecture tells you about the electron affinity, and the fifth on electronegativity, which is this. If you go through all those 5 lectures thoroughly, then guys, nothing can stop you from completing the topic periodic properties, classification of elements and periodic. properties. You will definitely be outstandingly answer any of the question that comes from this section in your IIT JEE mains paper. Okay, one more session I will be taking, which will be on the problems, the questions that have been asked in the JEE mains and advanced examination. Okay, so if you go through all such lectures, your topic is complete, and rest you can cover, you can learn. If you want to get more in the topic, then definitely you do join me on Unacademy. There I am taking the whole complete lectures. Okay, but yeah, absolutely here I try to cover everything overall, and I tried my best to give you the best out of it. Okay, so guys, whatever you feel, so whatever is your response, you please leave your messages in the comment section, so that I will be able to work on that, and I will be able to recreate my lectures in such a way whatever you demands. Okay, so here let's come to our last application, which is the bond length. Guys, as what happens with the bond length, as you have seen, if there is a species like HF, here we have the species like HCl, HCl. We have the species like HBr. So fluorine is 4.0, chlorine is, hydrogen has the same electronegativity values, chlorine is 3.0, then bromine is 2.8. So here, as the electronegativity increases, the bond length decreases. Why is it so? Why is it so? So what I just said is, let me repeat, if the electronegativity values decreases, the bond length increases. Okay, so here you can see that the electronegativity value, I'm just correcting myself if I'm wrong somewhere. Okay, so if the electronegativity values are decreasing, the electronegativity values are decreasing, this is 4, 3, 2.8, so the bond length was shorter, here the bond length becomes longer, here the bond length becomes longer. So what's the reason behind it? Okay, so what's the reason behind it? As the electronegativity increases, the electron gets more tightly held by the nucleus. So if this fluorine is very electronegative, this will hold the hydrogen electron more closely. Okay, if this will hold the hydrogen, because they hold the shared pair of electron now. So if this will hold the hydrogen electron more closely, then definitely hydrogen comes more close to the fluorine, and so therefore the bond length decreases. So we can say that as the electronegativity increases, the electron gets more tightly bonded, and so therefore the bond length, if you are talking about bond length decreases. Okay, that's why HF is smaller in size, HCl is quite bigger, HBr is more bigger, and HI is more bigger. Okay, so this is it, this is what we learn from this section. Okay, so ultimately we can conclude that electronegativity helps us in determining the nomenclature. Okay, electropositive will come on left, electronegative will come on right. Okay, just like you can take an example of NaCl, Na is positive being on left and the chlorine is on the right. This is the reason whenever you have an electronegative species, you have to put ide. If the electronegativity difference is greater than 2.1, then only a molecule is said to be ionic, and if the difference is less than 2.1, this is said to be covalent, and this is equal to 2.1, it could be anything. Okay, this could be anything. And the third point, acidic character, electronegativity increases, acidic character increases. Electronegativity increases, the basic character decreases. Or what is the last take from this whole section? Electronegativity increases, the bond length decreases. This is it. Okay, so its applications are much more important. And what are the factors that affects electronegativity? Percentage of S character, This is a question much important, and the oxidation state. This is it, guys. If you really like this session, then please hit like. This is what you could do for our efforts, okay, that we are taking to bring such meaningful sessions for you. Okay, so you do subscribe to the channel for more such videos which will keep on coming, and share this session if this helps you. This may help others as well. And you can follow me on Unacademy and use my code, which is Megha Mam, to get the Unacademy subscription or any other thing that you want to unlock on Unacademy. And if any of the session you want to see on Unacademy which could be unlocked, that can be unlocked by the code Megha Mam. And don't forget to follow me on there. See you guys. Have a nice day.